Right, I'm going to describe to you a very, very long-term project. You'll be amazed by how long this project has been evolving. It is the things that I'm going to describe here is the result of a PhD thesis of a spector who submitted a thesis and got the doctoral degree last year. And he's now working into making the thesis into a series of papers. The first one is published, the second one is submitted. It came back from the referee and he's putting in corrections and changes. And there will be a third one probably as well later on. The thing is that Oded is not working at the university, but he's working in the industry, so he doesn't have much time to dedicate to this project. Anyway, the start of this project is my PhD. I did my PhD at the Leiden University in the Netherlands, and it was good that I was allowed to do whatever I wanted. So I came with the topic of studying a sample of isolated galaxies and doing a multi-wavelength study of the sample. And this came out as a series of papers that were put together and handed in as a thesis to the university. And it was lucky that my advisor there, and you hear about him tomorrow, and we'll talk about tomorrow, he was broad-minded enough to tell me that I can do whatever I want. And just made sure that there will be a second advisor that will take care of the observational astronomy part, because although he was a good astrophysicist, he was not an observer. So this is the cover of my thesis, Isolated Galaxies, taken from the Big Parents, my adaptation. And these are the papers that came out more or less directly from this work. There have been many papers in between that are somehow related to this, but not deal with exactly samples of isolated galaxies. So, okay, we're talking about isolated galaxies. We have certain ways of thinking about such objects. We think that isolated galaxies are spirals or regulars, they are gas rich, they tend to be faint, they tend to be blue, they have higher star formation rates, specific star formation rates. This is what we normally think, although they are not star bursting galaxies per se with huge star formation rates. People will say, okay, they have high star formation rates, but not more than about 20 solar masses per year. So the question about isolated galaxies essentially comes down to how does the environment influence the evolution of a galaxy, the formation and the evolution of a galaxy. It is stated as the nature versus nurture in galaxy formation and evolution. So what I try to do, and my students also later on, is to try to compare the isolated galaxies with regular, field galaxies, not cluster galaxies, to see whether there are any specific differences in their properties. And now I'm going to speak in this talk, I'm going to speak about extremely isolated galaxies. Your thing is off.
No, it's
obviously.
It's the next form of blurring.
Okay, fine. So this is how the more or less how this talk will go. I'll do a little bit about the sample selection, then I'll do a comparison of the selected galaxies in cosmological simulations. And then I'll describe the observations and some conclusions at the end. I started with the only sample of isolated galaxies that existed then. It was created by Hooker and Planck, the late Hooker, and it's a byproduct of the first redshift survey, the for galaxies that was done at the CFA. They had redshifts, and they could select various types of galaxies. So from about 1,000 galaxies, they selected 12 that they called extremely isolated. So these extremely isolated galaxies were, the criterion was that they should have no other galaxy between 14 and 15.5 magnitudes within 45 arcminutes, whereas their average magnitude was about 12. So there's a difference of 3 magnitudes between them, 3 to 4 magnitudes between them, and the possible neighbors. And of course, in that paper, there are many caveats. What could other companions be, and whether they are really isolated or not. Anyway, my work was doing a optical, infrared, radio, ultraviolet observations of these galaxies, and presented these as example of isolated galaxies that have been hardly affected by their surroundings. The conclusion was, as we mentioned in this previous slide, that these galaxies indeed have star formation, not extreme star formation, but they all have star formation. So at this stage, and after publishing these papers, this was a state of the art. Then a number of other samples of isolated galaxies came around. One was selected by characterizing, and this is a very interesting selection criterion that uses the size of a galaxy, the size of its neighbors, and the distance between them. So the way that this looks like is that you select a galaxy, you see what its major diameter is, and you look in an area that is 20 times larger than the size of the neighbor galaxy. And if there's anything there that is between 1/4 and 4 times the size of that galaxy, then it is a neighbor, a companion. So that galaxy will not be isolated. The galaxies that fulfill all these criteria are included in what characterizing calls the catalog of isolated galaxies, CIGs. And the CIG is important because this is the basis of the Amiga selection that I'll talk about later. This criterion has problems because people who have checked it, and we also checked the galaxies there, they find definite neighbors. And the big shortcoming is that there's no redshift information. So it relies on the size of galaxies and projected distances, and it all relies on the optical. Although there is another catalog also by characterizing called TUMI, which is based on selection from 2 mass, but with the same distance and size criteria. Then the Amiga project, I hope you know about the Amiga project because it's a Spanish project and it's being probably trumpeted all around Spain by now. There is Montenegro, Arequipa. They have revised the catalog of isolated galaxies to throw out galaxies that may have companions. And this is their selection scheme. The criteria is that any possible optical counterpart should be further apart than 1 megaparsec in projected distance, and then the galaxy is considered to be isolated. There's also another criterion about possible tidal effects, but this is a little bit too complicated and I don't believe in it in any case, so I'm not going to mention it. The way that we decided to select our sample of isolated galaxies is to use essentially only redshift-based data, and considering all the difficulties of peculiar galaxies that can happen if you're looking towards a cluster where you have the finger of God effect, or very nearby us where you have 2 galaxies are too close and the cosmological expansion doesn't help much. The problem is that if you use NEB as the information of optical data, you're limited. So we decided we are going to add information in 21 centimeter using the alpha survey, about which I'm going to talk about in detail. And the criterion for isolation is no neighbors within 3 megapixels. So this is definitely much more isolated than the Amiga sample. In addition, it has a 21 centimeter criterion. There's also a limit in radial velocity because we didn't want to go too far and the galaxies become too small and you're getting mixed up with large scale structures that may come in. And we decided not to go beyond 7,000 kilometers per second. Okay, a little bit about alpha. Alpha is a survey that was done using the Arecibo telescope with the alpha receiver. It covers 7,000 square degrees. It covers this velocity range. And the detection of H1 is very good because you have a lot of protected area. So in a local group, let's say within a few megapixels, the limit is about 1 million solar masses of 21 centimeter neutral gas. The positional accuracy is better than 20 arc seconds, even though the beam is very large. The beam is 3.4 arc minutes, but you're centroiding it, and I'll show you some examples of how the thing looks like. The alpha receiver is a camera, essentially. It's a 7-pixel camera. It has 7 feeds, 7 receivers, a hood, very good, that sit in the focal plane of the 300-meter telescope at Arecibo. The moving power behind alpha and alpha is Marta Haynes and Ricardo Giovanelli. I didn't put a picture of Ricardo. I did put some of the things he likes much, and he highlighted also. The alpha survey. The way that this is done with Arecibo is that when the observations are taken, nothing is moving. The feeds are fixed. The arm on which the receivers are mounted is fixed, does not track. What happens is that the Earth rotates and the sky moves in front of the receivers. So this is called a drift scan mode. You don't get a lot of observing time, but you get something that is very uniform and doesn't have some systematic effects from moving things. In radio astronomy, there are various reflections that can come in. So if you don't move, you have the same effect everywhere, and then you can take this out. So the arm is rotated in some way that the beams track equal declination strips in the sky. So this is the way that the beams are arranged. And each one essentially samples the sky. You have the data is downloaded every 3 seconds or so, if I'm not mistaken. So you get a number of samples per source passage for each horn. The important thing of alpha is that the same part of the sky is reobserved after a few months, between 3 and 9 months after. So you get 2 observations. And this is very important because remember that the observations are done from a location on a sphere, the Earth, that is spinning, and this is a drift scan, but it's also moving around the sun. So the velocity vector to your target is changing from time to time. And this means that if you have a real signal, it will come at a different frequency the second pass. But if you have an Earth man-made signal, it will come at the same frequency. And there is such a thing that is well known. It comes from a Navy radar near Arecibo. And this is one, and there are also GPS signals that come in. But all these are excised, and in fact, there's a part of the frequency range that just by Doppler shifting due to the motion of the Earth can be covered in the second pass. So the drift scans were completed in 2012. A lot of observing hours. I put in about a month of my time at WSO this thing, and the data has been analyzed partly. It's analyzed all the time. This is how the data actually looks like. There's a bandpass, like a flat field, response over beams. This can be taken out, and then you get the corrected signal for this for the beam response. And here are some examples of how alpha signals look like. This is the velocity essentially, and this is the center of the signal. And you have here a strong signal, high signal to noise. The way that this is done is by central reading on all beams. And this gives you the 20 arc-second information. And then you compare what you have here with the sky picture. In the sky, you see that there is a galaxy here. So this would be the obvious target. If it already has an optical redshift, you compare it. If it doesn't, then the 12 centimeter signal is the redshift. So you get a lot of redshifts. Here's a low signal to noise thing that comes from this galaxy. Again, well centered reading. In fact, 20 arc seconds is the worst case. Normally, the position is much better. And here's another thing that alpha sees. This signal, for instance, is well detected, doesn't correspond to anything. This is what is called in the alpha jargon a dark galaxy. It has H1, but doesn't have a lot of light. It's possible that with deep optical observation, something will be observed there, and these things are being followed up. The final results, after waiting all this list of candidates and checking and whatnot, for 40% of the sky has been released, has been published. This is called the Alpha 40 catalog. And this is how the galaxies are distributed in the sky, where you have the SDSS targets and the alpha detections. And you see that there are indeed a lot of blue points that do not have a red counterpart. These would be galaxies that have 21 centimeter but do not have a redshift in the SDSS. So the first redshifts come from the 21 centimeter from alpha. And it looks like there is more of them in the autumn part of the sky than in the spring part of the sky. I should have said that alpha targets only the high galactic latitude part of the sky that is visible from Arecibo. Arecibo is at 18 degrees latitude, and everything that passes at 18 degrees plus or minus 16, I think this is the most that you can move in declination, and is in the extragalactic part of the sky, will be targeted by alpha. These are the sky regions where the search for the study I'm describing here. This is the spring region, defined like this, and the autumn region, defined like this. And these are the volumes that were sampled by this study. So I'm running a search on optical redshifts on these parts of the sky comes out with 33 galaxies that will be considered isolated according to the criteria we described before. No other combining within 3 megaparsecs. And the way that one chooses redshift is explained here. You have to use the most accurate redshift that is available. So you could choose either optical or 21 centimeter, or the best one that is available. So we came out with 33 galaxies, only using the optical redshifts. Now adding the 21 centimeter information eliminates about 1/3 of the sample, because the alpha information adds 21 centimeter neighbors that were not included in the optical survey. So the final sample has 14 galaxies in the spring and 7 galaxies in the autumn part of the sky. And these galaxies, 21 galaxies, were further divided into 3 samples. One is the first sample that has both optical redshifts and 21 centimeter redshifts, and no neighbors within 3 megaparsecs or more. This is the best sample, the first sample. It has 14 galaxies in the spring part of the sky, 7 in the autumn part of the sky. Then the second one that has only optical but no 21 centimeter would be no 21, no hydrogen there, no signal. So, but still there is a good redshift. This is the second sample. The third one that has it should have been rejected by having closest neighbor closer to 3 megaparsec, but we decided, okay, we are going to add these 10 galaxies just to increase the sample that we are working with, provided that the closest neighbor is more than 2 megaparsecs. So, indeed, when you look at the density, galaxy density versus distance from each of these galaxies, say for example, one of the galaxies, the first one of the spring sample, of the best spring sample, you see that there is no other galaxy to about 4 megaparsecs, and then you get other galaxies coming in. Whereas if you take a regular field galaxy, you see that there are more companions around it. And if you take M87, that is definitely not an isolated galaxy, you definitely have much more companions around. So it looks like the extreme isolated galaxies are located at the edge of voids in the galaxy distribution, and the nearest neighbor is between 3 and 4.5 megaparsecs for sample 1 and 2, and 2 and 4.5 megaparsecs for sample 2 and 3, for sample 3. So we then compared the other samples of isolated galaxies with what we have, the 3 samples of extremely isolated galaxies, by doing exactly the same kind of search for neighbors for all the galaxies in these samples. And this is the Amiga, the 2-MIG, the Karajansev, 2 mass derived sample. Log is something done by Karajansev's husband, Karajansev himself, the orphan galaxies, and this is a completely different type of survey, the void galaxy survey. And we found that indeed there are galaxies that will not be considered as isolated as our galaxies in all these samples. So all these samples have a lot of galaxies that are not isolated according to our criteria. Amiga, in particular, look, these Karajansev samples are mostly galaxies with neighbors. The void galaxy survey is derived in a different way by defining voids in the galaxy distribution and using something called a watershed algorithm to choose how the voids are located, and then looking at galaxies in the voids. There are some interesting objects in the void galaxy survey. For instance, if I remember well, there is one ring galaxy, polar ring galaxy in void that may be, say, a dividing wall in the void that contains that galaxy. So the probability distribution function, which means the chance of finding one companion at a certain distance, is very different between these samples. This is the extremely isolated galaxy sample number 1 we have here. Again, the nearest neighbor is very distant, and it's not like this for the other samples. So we believe that our sample is the cleanest one that would represent isolated galaxies in the nearby universe. So now we want to check these galaxies and make predictions of cosmological simulations. and we go to the people who do simulate the nearby universe. Specifically, there are two public data sets: the Millennium 2 simulation and the Box 160. And I'll talk a little bit about them. And from these data sets, we use our selection criteria to select a sample of isolated galaxies and to select a sample of randomly chosen galaxies. We assume that only some of the galaxies will have redshift information, because redshift information is important for our selection. So we have a mock isolated galaxy sample and a mock random sample, and we measure the properties of the two samples and compare them with what we know for our galaxy. Now, the Millennium 2 is larger. It samples a larger volume. It's about the same size, about the same size, but it has more particles, 8 times more particles than the Box 160. The particles are smaller mass than in Box 160, and the important thing in Millennium 2 is that it offers us something called a merger tree, because it follows how the galaxies have merged in the past. So you know when was the last major merger that a galaxy has encountered. And this is what we need, because we want to estimate for our extremely isolated galaxies when it is likely that they had a previous strong encounter with the galaxy that could affect its properties. So these are the samples, and this is a comparison of what the real life situation is compared to the simulations. This is the selection, our selection. This is the Millennium 2 and the Box 160 results, and you see that the fraction of isolated galaxies is very similar, and the same as the number of galaxies found. So, I mean, the percentage of galaxies found, density. So, from this, we conclude that simulations represent reasonably well the actual universes we observe, in which we observe our isolated galaxies. And here are things from the observations. These are the observed magnitude distribution of our galaxies. This is how Box 160 finds the isolated galaxies selected without criterion. And this is the same for Millennium 2. Millennium 2 has many fainter galaxies, and there is an ansatz that converts between the mass of a galaxy and its brightness, because this is dark matter simulation. It's not baryonic and stuff on the simulation. It's not a full thing. There's an ansatz that converts these to magnitudes. So again, the simulated extremely isolated galaxies tend to have no neighbors in their neighborhood compared with the randomly selected sample that does have neighbors around it, and the masses of the simulated galaxies tend to be smaller than the masses of the randomly selected galaxies. There are many comparisons that have been done between the simulations and the real situation. The thing that I spoke before, the merger trees that allow us to see when a major merger had taken place, allows us to say something about the extremely isolated galaxies selected without criterion from simulation. They tend not to have many merger histories in their past life. See here, they hardly have anything happening in the last few giga years. the probability of having a major merger during the last 3 GDAs was for the string sample of the extremely isolated is only 5%, whereas for a randomly selected sample of galaxies is more like 1/3 this major event accretion. Again, it's possible using the merger trees to know a little bit about the bits of matter that have been accreted by these galaxies. These are the sub-halos, and from this it comes that the extremely isolated galaxies accreted small bits of mass, 11 solar masses, in their last accretion event that happened a long time ago, compared with the random sample that has all kinds of masses. Now about the observations. The observations are done at our observatory. We have a 1 meter telescope that does not have a wide field of view. I told you about this yesterday, but it's a 1 meter and it has a very good CCD. This included imaging in white bands, BV and R and I. U is not useful because the observatory is not high enough, but it includes H alpha, and the H alpha is very important when we want to estimate star formation rates. So the optical data from Wise Observatory was combined with the alpha data, the 12 centimeter, and also with any kind of data in the literature that we could get our hands on. And here is an example. This is again the first galaxy of the spring sample, the best spring sample, which has both optical and 21 centimeter information. And what you see here is an R image, and an H alpha image, and a net H alpha image after subtraction continuum, of course. And when you combine these, you see where the H2 regions actually lie. On these two sides, not in the center of the galaxy. So we have this type of information for all the galaxies in our sample. And this allows us to determine what the equivalent width of H alpha is and what is the star formation rate. You see, it's not extremely high, it's not negligible, it's definitely something there, but not an extreme star formation burst. The question was, how these galaxies, how do they follow the main sequence of galaxies? And this is the main sequence of galaxies. And you see that most of them follow quite well the main sequence of galaxies, irrespective of which sample of isolated galaxies they come from. The colors versus mass of these galaxies indicate that these belong mostly to the blue cloud, with very few in the green band, none in the red part of this distribution. The same when you combine the optical with the ultraviolet data, they come mostly in the blue cloud, few of them in the green band. So that would indicate again that these are star-forming galaxies that have been forming stars. The H1 content tends to be lower for the most isolated galaxies than the less isolated galaxies. But again, it's not very significant. It's indicative. There is H1, but in the very most isolated galaxies, it is a little bit lower than in the other sample. The star formation against the hydrogen mass follows very, very well the relation found for alpha galaxies. So these are regular, you would say, regular galaxies, nothing special about them. In the morphology, looking at the images and doing the profiling these galaxies, we find that some of them are early type. They would not be classified as spirals, they would be classified as ellipticals. So some of them are early type, some of them are late type, some of them have been indeterminate morphology called maybe irregularness. The important thing is that for the early types, they do not have high H1 neighbors within 3 megapixels. So they do tend to be early types, even though they have hydrogen. So here are some examples of such galaxies. This is the one that I showed before. Some of these look like smudges. They would qualify as smudges, as Elizabeth Z called them, diffuse galaxies with either no H alpha or very weak H alpha. Some of them do show reasonably strong H2 regions. The extremely isolated galaxies that are early types look like early types. They don't look like spirals. Their profiles look like early types. Don't be fooled by these things because this is the center of the galaxy and you take into account the point spread function. So here are other early time galaxies from the best sample in the spring and from the worst sample in the autumn. They look like lenticulars, ellipticals. So here are the conclusions of this study. I remind you that this is based on a small number of isolated galaxies. What to do? Isolated galaxies are very rare, difficult to find, but this is the cleanest sample of isolated galaxies that we know of. What we found is that they do have normal mass halos. They did evolve without major events, at least in the last 3 to 4 gigayears. They were not disturbed or perturbed by interactions with other galaxies. So this would be the way that a normal galaxy should evolve. And so the conclusion is that the star formation rate is not influenced very much by the environment, unless one is in a cluster. In a cluster environment, that definitely would be affecting the star formation rate. The colors of a galaxy depend mostly on the stellar mass. This is what we found. And the amazing finding is that the most isolated ones have a high fraction of early time galaxies, not spirals or irregulars as one would have guessed initially. Now, this is a bit revolutionary because it contradicts the first statements with which we have started this talk. So, as I told you before when I came, one has to be skeptical of all kinds of claims, including those from observers. So, one would look for supporting evidence completely, from a completely different point of view. And luckily, this exists. This just came out. I just saw this a couple of days ago on AstroPH. This is a talk presented at the EAS meeting. They looked at early time galaxies, isolated early time galaxies, and they found that the isolated early time galaxies have H1. A significant fraction of them has H1 gas. If they have H1 gas, they probably also have some star formation. Since this was only an abstract, this is not yet clear. So isolated galaxies can be early time, and some of them can even be star forming. But morphologically, they would look like ellipticals. So you should now go move your thinking into how elliptical galaxies form traditionally. Because traditionally, people will tell you, we know how elliptical galaxy forms. Two spirals collide, different spins. What you get is an elliptical galaxy. But here's a case where this is not the case. This is not it. An elliptical galaxy can also form when matter is accreted into a dark matter potential with different directions. So you have different angular momenta of different blobs, and when these mix, you can get an elliptical distribution. The theoreticians have not yet given their verdict about this, but this would be my guess. That's it.
Okay, thank you, Noah. Okay, go ahead.
No. Hold on.
So you have the slides, because I'm going to give you the slides, so you can have the slides. I put them there because the video doesn't work. And then if you have any questions, then you should either write them or talk to me here.
You asking me?
I didn't have a specific question, but looking at this, I'm thinking, so maybe you would find these closed surface right now start forming extended, start forming regions around this guy.
There are so many interesting topics to work on. One has to be very critical and choose very carefully what to do, otherwise everything goes to hell.
But do you see actually early types with extended?
The images that we have are not as deep as the ones that I'm using for visual balance. It all depends on Mr. Dr. Spector, whether he wants to continue to work on this thing, because I told him, there's this telescope, you can get observing time and look at your galaxies, very deep. We'll see.
Where has he gone?
Well, his family has a company, and he's essentially the top technical person. He's very busy doing automatic fire extinguishing systems.
Interesting.
No, I have a curiosity. I don't know whether you have already talked about that at the beginning of the talk, but is there, if you take one of these filaments in the cosmic web,
Yes.
there is any trend perpendicular to the filament in the shape, mass, or properties of the galaxies?
No work has been done from now. And it's very difficult to trace the dark matter filaments. It's very easy to detect them in simulations, but trying to find them in surveys of galaxies is difficult.
That's, you have this, correct?
Yeah. Look at these redshift versus position maps. You have various structures there. So all these structures are either clusters, where you have a finger or dot effect, or the walls, the giant walls. And in the walls, it's very difficult to say whether there's any motion perpendicular, because the filament is determined by the redshift. You need to have an independent distance estimate, like a tip of a red giant branch that works only for nearby galaxies, or the fluctuations in the surface brightness. But this work has not been done in the nearest walls, that would be the Perseus. Perseus wall, about 7,000 kilometers. So this is too distant yet. Maybe with a large telescope, WSO-UV or something else, it would be possible.
Here is some measurements. The spatial correction. Have you applied some
Yes.
Yes.
Yes, we have, yes. I think that what we did is standard exactly extinction law.
You have it with a finger or something?
It has been done on all on the program and the chart. Yes. But these are not highly extinguished galaxies.
No more questions? This side to know again. We are going for that. If any one of you wishes to join us, you are welcome. You can